Hi, my name is Mounsaveng, and in this video I'm gonna present you our work called Bag of Tricks for Full Test-Time Adaptation. In image classification, deep neural networks perform well at inference time when test data comes from the same distribution as training data. However, they become inaccurate when there is a distribution shift. In this case, domain adaptation techniques provide a remedy by enabling the models to leverage the knowledge learned in one domain and apply it to another. In this work, we are gonna focus on a particular setting of domain adaptation called fully test-time adaptation. In this setting, what we have at disposal is only a pre-trained network and unlabeled data from a shifted domain. One particular characteristic of this setting is that it is online. Data is received as a continuous stream and is processed as it arrives. We are gonna investigate tricks and techniques from 3 state-of-the-art fully test-time adaptation papers. The first paper, 10th, is a seminal work in fully test-time adaptation. In this paper, authors propose an adaptation method based on entropy minimization. In the second paper, the authors investigate different architectures, normalizations, and propose a method called SAR, which performs an entropy-based sample selection. Finally, in the third paper, the authors propose Delta, which is a method to rebalance data online. What we observed is that if the method proposed in the 3 mentioned papers are bringing a very good improvement of the model performance, results are obtained using combinations of different tricks and techniques. Therefore, it is very difficult to really identify and understand the impact of each single one of them on the model performance. So, the goal of our research is to disentangle the tricks used in the selected methods to evaluate empirically the impact on the model performance. We will also focus on small batch sizes, so smaller than 16, to be closer to real-life scenarios where the data is received as a continuous stream. The tips and tricks we are gonna investigate can be classified into 4 groups. The first group, called architecture and normalization, relies on the idea that batch statistics are unstable in case of small batch sizes. The idea behind the second group, called class rebalancing, is that an imbalanced data stream can lead to a model collapse towards the dominant class. The third group focuses on sample selection, with the idea that samples with a high entropy can lead to a degenerated model after adaptation. Finally, in the fourth group, we investigate the important concept of calibration, which has a direct impact on the model adaptation as it modifies the entropy of the prediction. Let's take a look now at some results. For architecture and normalization, what is interesting to see is that the accuracy of a ResNet 50 architecture with batch norm is dropping when the batch size becomes very small. This can be compensated by using batch renorm instead. However, the most stable results are obtained by using batch agnostic normalization layers like group norm or layer norm, and the best results are obtained by the transformer-based architecture with Bayes. For class rebalancing, what is noticeable is that ResNet 50 with batch norm has difficulties to maintain a good performance level when the data become very unbalanced, even when using class rebalancing methods. Using a batch-agnostic normalization layer combined with a class rebalancing method yields the best and most stable performances. What we can also observe is that DOT is performing better than SAR when the imbalance factor is low or average, but shows its limits when the imbalance is too strong. From our experiments concerning sample selection, what we can remember is that fine-tuning the entropy selection threshold can lead to a significant increase in the model performance for all architecture and all batch sizes considered. Moving on now to the experiments focusing on calibration, what is interesting to observe is in this table is that applying temperature scaling during adaptation improve the model performance or certainty. What happens now if we combine the presented tricks? In the results presented previously, what we could see is that each single trick used separately can already improve the model performance, but there were some corner cases. The best results overall are obtained using a combination of all the tricks together. In this table, we can see the accuracy of the model for each adaptation method. What is interesting to notice and remember is that combining the selected tricks leads to performance improvements compared to the selected fully TTA state-of-the-art methods. To conclude this presentation, we explored the fully test-time adaptation problem when dealing with small batch sizes by analyzing different tricks and methods. Each trick can already improve the model performance separately, but using combinations of them yields the best model performances. Moreover, using group norm instead of batch norm with ResNet 50 yields more stable results for the same amount of parameters. And finally, using an entropy-based sample selection method reduces the computational burden by using fewer samples to adapt the model. Thank you very much for your attention. For more results and details, we invite you to take a look at our paper. The code used for our experiments is also available on GitHub.